It's a pleasure to have Lara. She will continue on cluster structures on flag varieties and applications in particle physics.
Thank you. Yeah, so I cheated a bit. I put down the example that we ended off with yesterday. So we finally got to the point where we see the cluster structure on partial flag varieties. I told you how to get the quiver for this cluster structure, and what was missing was the cluster variables. So just to remind ourselves, if we have a partial flag variety, to get this pseudo-line arrangement, which is like the gadget that will help us to get the seed, we draw the numbers 1 to n on our x-axis, 1 to n on our y-axis, and mark the points that correspond to the support of our flags. And then there was this rule that we draw pseudo-lines, and within this block from 1 to d1, and then d1 plus 1 to d2, etc., the lines don't intersect, but just go up, do one turn, and end up in the corresponding slots here. And additionally, we wanted the first block to map to the last block of lines here, and then continue accordingly. So this was the example 2, 4, 5. And we already saw how to draw the quiver associated to it. We had the correspondence between mutable vertices and bounded faces. Frozen vertices, we had 2 types. The one type was faces unbound only to the left. So of this form. And the other type was one extra vertex for every element of our support vector. And then the rules for arrows are depicted here. We go downwards if 2 faces share an edge, or from left to right if the edge is vertically. And then we go diagonally through crossing of 2 edges. So if 2 faces share a vertex, we have these diagonal arrows. And then there's extra rules that I didn't specify to add the arrows to these extra frozen vertices. But they will always, like generically, they will be of this form. So when we have the crossing of a line di with the line di plus 1, then there is one vertex frozen corresponding to di that connects the upper left face with respect to this corner to the lower right face. Okay, so then now we can move on to the cluster variables. And the first thing to do for the cluster variables is read off index sets for every face in this diagram. And so for cluster variables, also step 1, we read off index sets that will be subsets of 1 to n. IF, and that is for every face of my pseudo-line arrangement. And the rule for reading them off is I record all the indices of lines that are either north or east of my face. So if I do this, for example, here, let's start here. This one just has the line 5 northeast. If I move over here, the line 4 is also above. Here, additionally, I collect 3. I collect 2. Here, I remove line 4 because now it's to the left. I remove line, oh no, sorry, I'm reading off the indices wrong. I'm reading up, wait, oh no. No, it's correct. Yeah, 5, 4, yeah. Yeah. Sorry. The indices of the lines are the endpoints on the y-axis. Right. So I go here. I remove the line 5. And finally, over here, I only have the line 3. And this one is 3, 5. Okay. So IF contains indices of the lines. And the index of the line is its endpoint on the y-axis. For all lines passing northeast of my face. Okay, now these index sets correspond to minors, but they're not yet the cluster variables. So these index sets, we will define minors associated to them. And it will be minors that have this index set as the rows. And for columns, so we're thinking here of minors of an n times n matrix. And the index set will index me a collection of rows. And for the column set, I will select the last as many columns as I need. So this will be the minor with row set IF, and the column set is, so I have to take n minus the cardinality of IF plus 1 until n. Right, so these are the last as many columns as cardinality IF. And these are minors that live in the coordinate ring of my unipotent group. So this was n minus, and let's just stay in the example, 2, 4, 5. And we've seen, so is this clear? Maybe pause a second for the combinatorics. Right, so every phase has this index set associated with it, and from that index set, I can build a minor of an n by n matrix that is also a minor of an n by n matrix with certain restrictions on the entries, as are the elements of this group. And this is my element. And we've seen in Yevgeny's talks, and also I repeated briefly yesterday, that there is an inclusion. We now should do it more generally. There's an inclusion of this group in my flag variety that is really just taking the row span along my matrix of a point. And this gives me, on the level of coordinate rings, a map in the opposite direction. So what guys Leclerc and Schrawan show is that I can actually lift these, and every such minor has a unique lift in the algebra that I'm interested in. Okay, so I look at the pre-image, and there is a unique pre-image that is homogeneous with respect to a grading on this algebra, and that's the algebra, that's the element I choose. Right, so in general, there's a whole bunch of elements here that project down to a minor. But in this class, I can look at the ones that are homogeneous elements with respect to the grading, and that's the element I choose. Okay. Right. So in the flag variety, I have my favorite set of coordinates. So this is the Plücker algebra flag variety. So I have minors, Plücker coordinates, that correspond to index sets of cardinality D1, D2, or dk. While as if I go to my diagram here, you can already see in this example that I get minors of all kinds of sizes. So for example, I have minors that are just matrix elements, but my flag variety did not have 1 in its support. And also for 3, another example. So these are not Plücker coordinates, which are my favorite minors in the Plücker algebra. So let me write this down. This is Guy's Leclerc Schrer. But yeah, it's actually not hard to see this, but still. Every minor. Okay, let me change notation here so that I have delta for the lip. So D, I, F in this algebra has a unique, homogeneous lift delta IF in my Plücker algebra. And this is the collection of cluster variables. So now I have my definition, or yeah, this delta IF for F a phase in my pseudoline arrangement is my initial cluster. Okay, so let's look at these minors and what they actually are in terms of Plücker coordinates in this algebra. So first of all, we can observe one thing about the index sets that we get here. And that is that in fact, if we, that they're always union of 2 intervals. So this means there's always consecutive numbers and at some point there's a jump, right? So for example, here, this would be 2, 3 as one interval and then 5 as another one. This is just one interval anyway. And then here again, I have 3 and 5, 2, 3. Okay, this is a small example, but this is not hard to observe in general. So they're always of form ij, dj, and then ij plus 1, dj plus 1 for some indices ij that are, for the first one, less or equal to dj. So dj and dj plus 1 are 2 of my support. So my dimensions in my flag. And for this to make sense, I will set d0 to be 0 and dk plus 1 to be n. Maybe actually I don't need d0. I think I don't need d0, but yeah, okay. Okay, so the index sets in my initial seed are actually always of this form. And then I have the following formula. And let me state that as a proposition. I will need the following value. N is n minus dj minus dj plus 1 plus ij plus ij plus 1 minus 1. And then my minor associated to this index set. This is true, yes, for this specific initial seed that I've drawn, this is true in general. Yeah, it's a bit of a stretch to observe it from this example. Yeah. Okay, so, but actually already here, I mean, you can also see it from the combinatorics kind of, because your lines always move in these blocks. Whenever you move along some faces, you can always just add or lose lines which come from one block. And that's kind of the dynamic. You're always in between two of these DIs, and maybe all the complete block of lines before, or yeah. So that's kind of the idea if you move in this diagram. Okay, so this is now the following expression in terms of Fluker coordinates. I have a sign here. Oops. And then I have two Flukers. So for the notation, when I write this expression, I mean the interval that starts at 1 and ends at this value. Fluker coordinates are also minors, and they are exactly those minors where this is my column set and my row set starts at 1. So here, 1. So what this does, and maybe let me write what is J. Let me complete the sum. So what this does, or what is this formula actually? Well, if I consider this as an element of just this ring, then it's just a minor on a matrix. And what I'm doing is using Laplace to change from minors that are column bound to the end to minors that are row bound to the top. So the proof of this statement is just use Laplace. So we use Laplace here just on matrices, and then we homogenize, because in this space, remember this one was 1 on the diagonal and then some non-zero entries below. No, oh, actually I wanted n plus. Yeah. Sorry, n minus was Yevgeny's convention. So first of all, if these are my matrices, then these minors actually give me interesting information, right? Because they are always taking place here. They're always bound to the last columns, which are the ones that have interesting entries. And then here I can use Laplace, and then I homogenize with these Fluker coordinates that start at 1 and go to some value, because these are all 1 on these matrices. Okay. Yeah. Yes. Yes. Okay, so this is maybe I do need the zero. So this is the generic situation. We can draw the diagram for the Grassmannian. Grassmannian 2, 4? Yeah. Yeah. Yeah, so I think so these segments are the generic values you get. Maybe I should add 0 somewhere. Maybe I should add 0. Yeah. So there's many minors that actually just have one interval, right? All along the boundary, for example. All the frozen ones are always just one interval. And I also have the 2 extra frozen ones that don't come from interval. So for the Grassmannian, that would be 1 extra one of this form. Yeah, I mean, let's, so this is my diagram for the Grassmannian 2, 4. And then I have 2, 3, 4, 3, 4, 4, 2, 4, and that's it. And the 1 extra, which is 1, 2. No, exactly. Yeah, this is all kinds of cardinalities between 1 and n minus 1. Yeah. Yeah. And afterwards, on the right-hand side, my expression should have the right cardinalities. So here I only want the cardinalities to be di. Or, okay, to be cardinality inside this tuple. D1 to dk. But also these are probably, we can already say it from the dj. Can we say what's the cardinality? Well, okay, yeah, we could count. Like j has this cardinality, and then we take this interval and okay, it's possible. Okay, so great. So now we have yes. Yes. This is a count. What is the count? So ij, dj, j is the sum from q equals ij to dj over q plus the sum over all the j's in j. Right, so it's summing up all the numbers in this first interval and then all the numbers that appear in this one. So it changes with every term and flips sign depending on the elements here. No, so here this is strictly smaller. It can just be dj plus 1, and then the whole thing is just one interval. That's possible. Yes, I mean, so what I tried to do here is have like a closed formula that would include also these non-generic cases when this is just one interval. Right, so dj plus 1 equal to ij plus 1 is possible. And then I would be in one of the cases where I just have one interval. So my index sets are at most. Right, yes, yeah, I have, yeah, I can then write it as this interval and this is empty or the other way around. And yeah, I see. It's fine. No, it does not affect the formula. The formula just corresponds on the set, not on the decomposition. Yeah, because this is just the minor, and once I look at the minor, I don't distinguish anymore where my rows or columns. Okay, let's then complete the example and write down the Flickr expressions that I have here. Okay, so I have delta 4 is P45, delta 5, P15, delta 345, P1, 2, 3, 5. Okay. So yeah, what can we observe? First of all, after doing this transformation, we only see index sets of the right cardinality, only 2 or 4. We have a bunch of variables that are just index sets. And then we have 2 that are quadratic, that are just Plückers, and we have 2 quadratics. And one general fact is, in this initial seed, we will have quadratics appearing as soon as there is a gap in my tuple of indices. So let's say this initial cluster contains only Plückers. Coordinates, so only Plücker coordinates, no degree 2 expressions, if and only if di is di minus 1 plus 1 for all I. No, yes, yeah, plus 1. Okay. Okay, a question? Hmm. I want to say no, but I would not know an argument right now. Like the initial seed certainly just has already degree 2 elements. Yeah. And by experiment, once you start mutating, degrees grow rather than not. But I don't know if it's known that there is not a single seed containing only Plückers. Right. But so the Grassmannian is in this category. Right. So if, let's, oh yeah, okay, maybe, I don't know if I should change the statement. Say or K is 1. Yeah. Yeah, but as soon as there's one gap, and I mean, this is a very small example where there is a gap and we can see this phenomenon happen. Okay, so the theorem of guys Leclerc and Schrer is then that there's an isomorphism between the cluster algebra associated to our quiver with this set, and I don't think I wrote notation. Let's write this here. With this set of cluster variables, by tensored with the complex numbers, is isomorphic to the Plücker algebra for my slag variety, or the homogeneous coordinate ring for the slag variety with respect to its Plücker embedding. And guys Leclerc and Schrer showed this statement. I mean, now we did the type A construction. They showed it for type A DE, I believe, and it's also been generalized to other types. Unfortunately, I forgot the name of the author. That's quite recent. Does anyone remember? Sorry, I'll add it to the notes. But this is also, this is known for all types of partial flag varieties. Okay. Great. Yeah. Compatible with the. Mm-hmm. Yeah. Don't they? I'm not sure. To be honest. I don't know. that are not crossed. Yeah, I don't know, but it would be interesting to look at that. Yeah, so I know one statement about cluster compatibility with another cluster structure, and that's the following result, but it goes to Grassmannians and not to full flag varieties. So let me say that. Or before I define, let me find a map. Yeah. Okay, no, I can say it here. Okay. So here's something we can do with this cluster structure. We consider the partial flag variety any, U1 decay n. And let's have local coordinates here. Let them be denoted with the capital P's as we had so far. And then we also consider a Grassmannian dk capital N, where this capital N is my small n, and I'm adding the difference of d1 and dk. So plus dk minus d1. And Fluker coordinates will be denoted by lowercase j's, pj's. So these are all dk element subsets of 1 to capital N. Then combinatorially, there's many ways how I can get from an index set of cardinality sum of the di's to an index set of cardinality dk. And that defines the map. So I take a Fluker coordinate of my flag variety, and I send it to a Fluker coordinate in this Grassmannian by filling up my index set. This index set could now be of cardinality d1 to dk. If it's already dk, I don't have to do anything. But otherwise, I can fill it up. And I will do that by adding n plus 1 until n plus dk minus the cardinality of I. So just the right numbers that I need, starting from n plus 1. And this very naive map turns out to extend to an embedding of the Fluker algebra for the flag into a Fluker algebra of the Grassmannian that is a cluster subalgebra. So in particular, this means, or what is the proof of the statement, that in this cluster algebra of the Grassmannian, there exists a seed in which I can do a sequence of freezing and deletion to get the initial seed for the flag variety. Exactly, yeah. So I go to some seed here. This is much bigger. The dimension here is larger than the dimension here. So I have to get rid of several vertices, and I have to find a seed, or there's a seed that contains all the images of the cluster variables for the flag. and some other things. And it is such that after freezing, I can do this process of restricting, and the cluster structures are compatible. So geometrically, there's one subtlety. Geometrically, we can go to the affine cones of these spaces and we're fine. But then the flag variety and the Grassmannian are obtained by different quotients from their respective affine spaces. So these algebras have different grading, and going from here to here, I lose the multigrading. So this does not give me a statement between the projective varieties. So my collaborator, Zhenrong Li, together with a former student of Lauren Williams, they're investigating the question if the cluster structure that I get here corresponds to the cluster structure of a positroid. But I don't know what are their results, I think. Oh, this paper, I mean, yeah, we finished it last year. Okay. So here, so this is some index set that its largest entry is at most little n, lowercase n, and I will add n plus 1, so a sequence, an interval starting at n plus 1 and ending at the number of variables I need to add, and this is n plus dk minus the cardinality of ij. So actually, when we started this project, we were first interested in only two classes of partial flag variety that appear in particle physics, and I will mention this a bit in the rest of my time. And there we actually did a different embedding. So if you are in a case of two-step flag varieties only, then you can also add the interval here that goes all the way until capital N. So maybe I can add this. So if k is 2, then I can also write here n. Okay, now I want to go until capital N, and this is then is capital N minus the cardinality of I plus 1. Then this also works. And I think my student worked on the case of 3-step flags with this embedding, and it still works. But combinatorially, this one is nicer. And it's also, yeah, maybe it's also not hard to see why. So if we go to the Grassmannian, or if you know the cluster structure of the Grassmannian, you know that the initials, like for this nice rectangular initial seed, all the index sets are intervals or union of two intervals. And if we do this, then our index sets are naturally of that form as well. While here, because this could be a union of two intervals, we might have 3 intervals in total, and it becomes more complicated in the Grassmannian to find the right seed. That was the idea. Okay. So the proof here, just last comment. Proof, find a seed in here. That restrict to the initial seed. Of the flag, right? Okay. Right. Right, so then you would go until n minus 1, and you have to add n minus 1 minus 1. So you have to add n minus 2. Right. So you go, so if you have 1 to n minus 1, this is the k, and then I have to add n plus dk plus minus d1. So it's n minus 2. Two n minus 2. Yes, twice n minus 1. Yes, yes. No, but to be fair, this was not the, I didn't study this case particularly, so I don't know what that could mean. I mean, maybe you can already see it can you see it in the matrices? So you have n minus 1 times n minus 1 minus 1. Yeah, maybe, because you have two matrices like this, maybe one of them is already giving you the flag. And I don't know, but I didn't look at this case. I'm just guessing here. Okay. Okay. I have about 15 minutes for about 6 pages in my notes. That's not going to happen. But I wanted to tell you a bit of an application of cluster algebras that has been coming up over the last, by now, 15 years in particle physics and scattering amplitudes. And this theorem that I presented was actually very much inspired by physics, in the sense that there is cases where these spaces have an interpretation as configuration spaces, and some physics limit process indicates such an embedding in these cases. So what we did was very much inspired by this physics observation, and then generalizing it to all partial flag varieties. So this result turned out to be then important in applications, and also the result that related the tropicalizations of an ideal with the tropicalization of a Fock contour of tropicalization of a cluster variety. So let me tell you a bit about where we're going. So what's the scattering amplitude? In very rough terms, this is a function. So we're going into the world of quantum mechanics, where we no longer have Newton's laws, we can no longer do any predictions. Everything that physicists do here becomes probabilistic, every model is probabilistic. So if we do some scattering process, like an ICERN in Switzerland, then we can no longer, whatever the setup of the experiment is, it's no longer possible to predict the outcome of the experiment. So we can always just probabilistically say what could be the outcome. And the scattering amplitude is a function that takes in a certain configuration of particles and tells me what is the probability that this configuration is the outcome of a scattering process. So configuration space is a space where a point corresponds to a particle configuration. And this function is proportional to the probability of the configuration so this is a point in my configuration space. Occurs as the outcome of the scattering process. So mathematically speaking, scattering amplitudes, well, of course, they have been studied also mathematically for many years, but they're rather nasty functions. In general, they're infinite sums over integrals. Every integral is a Feynman integral, and Feynman integrals themselves are not that easy to compute. But there has been recent work over the last 20 to 30 years of changing the parametrization of these configuration spaces, actually passing from the four-dimensional real vector space, Minkowski space, where particles and we actually live in, to projective spaces. And that's called twistor theory or twistor spaces. And with that came new ways to express these functions. So after going through that process, mathematically, we can now say that scattering amplitudes are multiple polylogarithms and those are expressed or can be expressed as iterated integrals. So here's a very simple example of what a multiple polylogarithm is. It's the function Li, a generalization of the usual logarithm. And I can write Li of z as a sequence of integrals, define it recursively. This form. Okay, so this is one way how physicists now compute these functions, but it is still relatively nasty because we have a sequence of integrals, and even if we know the integrand, it is still a hard process to actually compute the integral. So Goncharov and collaborators, or just Goncharov, studied these functions for many years, I think starting in the very early 90s. And there's several papers that discuss algebraic structures on these spaces. There are shuffle algebras, depending on some parameters. There are certain hop algebras. So there's a variety of algebraic structure here. And one of the outcome of this extensive analysis of Goncharov is the symbol map. So what does this symbol map do? It takes a multiple polylog G, and it sends it to its symbol. So in order to tell you where this lives or what it does, I have to think of G as a function on some space. So here G is now a function on some space M, some variety. And then this SG lives inside the tensor product of invertible analytic functions on M. So just a bit of more notation, and then I'm gonna tell you a bit what's going on and why am I mentioning these things that are apparently so far from algebra besides the shuffle algebra hidden somewhere. So the symbol of a polylog is now some tensor product in some vector space, and we call the elementary tensors appearing here words, and the actual functions that are part of these tensors, the factors, we call them letters. And then the set of all letters that I get from a symbol is called the symbol alphabet. Okay. So now how do we get to cluster algebras from this mess? Well, the thing. Yes. No, so I mean the components. So the actual functions that appear inside the, like, as tensor factors. I don't know what's the right word. Yeah. So this is the sum over some elementary tensors. And these VDs that appear in this expression, those are the letters. Yeah, I don't know how to call them. Like the elements. So not the, so let's say so if this is my symbol, then the words would be these, we call them I over some index such I. So these words would be the elementary tensors, where the coefficient is non-zero, and the factors would be all the Vij's, such that their Ci is non-zero, and this is one of the functions that appears in my tensor product. I also don't like this word, but I don't know if there's another terminology to refer to it. Right. Okay. So the letters are the VIs that appear in the words. The letters are the symbols the words are made of. And then there's some relations also happening here. So this is not unique. The shuffle algebra structure I have on the space of functions induces a shuffle product here, and that gives me relations between the expressions. So there's not a unique way to write down the symbol alphabet. That's always up to the relations that hold. For example, the shuffle product. But yeah, as I didn't define generally what is a multiple polylog, this also does not really make sense, but it's in the notes and I'm happy to tell you if you want to know. Okay, so how do we, what's the idea here? Well, first of all, this tensor product is something that is easier to deal with than the original function. There is a whole theory of, given a symbol, how do you get to the function? It's not easy because you have to determine, well, the coefficients, because you lose in the symbol alphabet, the symbol, you forget the coefficients. And there's a whole theory there, and it's highly non-trivial. But still, there is a bootstrap program that showed in several cases that if you know enough about the symbol, there is a unique function with this symbol in your space. So it is therefore very interesting to understand what are the symbols of scattering amplitudes. And here's the kind of roadmap. So we start with some physical model. Let's call it M of n, n being the number of particles. I go to the configuration space, which naturally lives in R to the 4. So if you didn't know, we're living in R to the 4, not R3. The fourth dimension is time, and this space has an inner product with this signature. So this is naturally where you would find a particle configuration. Then there is twistor theory that was introduced by Penrose. And it essentially, summarizing very briefly, gives us sensible isomorphisms between this 4-dimensional real space and four-dimensional complex vector spaces or subspaces. In particular, when going through this process, we end up with a projective variety, complex projective variety. So we get, and these are the ones that are known as configuration spaces, and we live in some P capital N, yeah. And this is a projective variety. Great, so once we're here, well, what happens, we can, the scattering amplitude was a function here, it's still a function here, and we change the coordinates that it comes with, and we express it in these new coordinates. And one of the advantages of this theory is that the expressions as a function on the projective space become way simpler than the expressions we had here. And there are certain symmetries of the configuration spaces that are easy to detect here from the projective variety structure that are hard to detect here. And there's other advantages that came out of this very potent theory. And so here we now express the amplitude in the coordinate of this space. And then we compute its symbol. Let's call this A. And alphabet. Now, oh, the laptop died again. I have 3 minutes, right? So the surprising thing that happens is that on this level, we see spaces that are very familiar with us, for us in algebra and algebraic geometry. So for example, if we start here with a certain model that is called n equals 4 super Young-Mills, then this variety is the Grossmannian 4n. And it turns out that if we jump over here to the symbol, and we assume that we're only having 6 or 7 particles, then the symbol is the set of cluster variables for the Grossmannian. And this is work, this was the first work where Goncharov introduced with Markus Spratlin, Anastasia Vulovic, and Virgo, I forgot the first name, the symbol map for scattering amplitudes, and they found these results. Now, the super here indicates that this model assumes supersymmetry, which is not actually happening in our world. So it is actually more interesting to go to another model, QCD, or quantum chronodynamics. And maybe I should also mention there's n equals 8. You can still recover the alphabet from the cluster structure, but this is an infinite cluster algebra. So there's other types of letters coming up, and there's other kind of constructions you have to do, but you can still recover the alphabet. And it's actually also mathematically very interesting because you have to do like infinite mutation sequences and take limits of the cluster variables that appear and fun things. So QCD is part of the standard model. Standard model refers to the actual world we live in. And if we go over here, we find there's 2 ways we can go through this twistor theory black box, and we find partial flag varieties. 2 4n and 2n minus 2n. And then we can jump over here. And what we found is for n equals 5, we have the same nice result as up here. The alphabet consists of cluster variables. And this is when I entered this story with James Drummond and Ross Glue. And here should I say Goncharov. And for n equals 6, we have partial results that go in a similar direction. And these are results from this year, so this case is very much not well understood yet. And that's it. I think I'm out of time. Thank you.
Any questions, comments?
Oh, so I'm taking the lift of a function, not a matrix, right? So I had I had this as elements in here. Yeah, let's just write it like this for simplicity. And I have a surjection of the homogeneous corner ring of the flag variety. And then I take a certain pre-image here. There's many functions that would lie in this pre-image, and then I choose this lift to be homogeneous. So if you would like to draw this minor on a matrix, it still looks the same. It's still the same minor, just that I change. So if I work in this ring, then and this is also, whenever I think about a minor in here, I will think about how that minor acts in this big open orbit that is just given by the matrices in N+. Ooh. Mm. Yeah, I don't know. Yeah, maybe my way of thinking about this is very naive, but whenever I deal with cluster structures, I'm kind of assuming I'm in a big open orbit inside of my space. So I don't really change the matrix. I would not know how an interpretation like this could be. It's unique after I add the assumption that it is a homogeneous element.
Maybe you already said this, but maybe I missed it. This partial flag variety coordinate ring being a cluster algebra tensor with C. So the cluster variables or the cluster monomials, is there a geometric interpretation on the flag variety side?
Oh, I don't know. I mean, there is for the Grassmannians. I think that's what Jean did. If there's a geometric interpretation of the cluster variety, the cluster variables in the flag. Yeah, I don't know if of an extension of this Grassmannian result to the flags or to arbitrary flags.
Any more questions? Okay. If not, let's thank Lara. So on behalf of all the organizers, we sincerely thank you for your, So actually, like, she accepted our invitation in very short notice. And then, like, still she like gave very well prepared lectures. Okay. I sincerely thank you for that. Yeah. Thank you.